Hi, I'm Jim Carroll. Today I'm at Stanford University talking to Dr. Leonid Kazovsky, Professor of Electrical Engineering, and thank you for speaking with me today.
Glad to talk to you.
It often seems that the wireless and the optical networking domains are completely separate. The different standards bodies, different trade shows, different vendors in each of those spaces. Could you tell me about your work that you're doing in a hybrid mode where wireless meets optical?
Right. The point is well taken. Indeed, up until now, these two network domains, optical and wireless, were completely separate. There was really no interactions between, or almost no interactions between people working in these two domains. And probably for good reasons. There was probably not much need for close interaction and close integration. But I believe that in the future this will have to change, because optical networks are beginning to become or to penetrate a smaller geographical area. So optical access networks are becoming much more common, and optical networks within buildings, both within residences and office buildings, also becoming much more commonplace. So as these two domains are beginning to overlap geographically, so to speak, I think it is inevitable, or almost inevitable, that they will have to interact with each other tighter. Because if you continue to keep them completely independent from each other, we will lose many of the efficiencies one can gain from integrating them tighter.
So initially, wireless is being served by the optical network in a backhaul capacity, right? So everyone's racing to deliver gigabit Ethernet or deliver fiber out to a cell site or to a tower. Are you seeing a deeper level of integration that could or should happen in that space?
Right. I think the need for integration, in a sense, grows as the size of the cell drops. So if cells become smaller, then the need for tight integration between photonics and wireless domains becomes greater. Just to give a simple example, one area that is very popular among wireless people is coordinated transmission. So coordinated transmission by its very nature requires coordination between several antennas. So, and that in turn implies that there is some medium behind these antennas that allows them to coordinate their transmissions. And that medium has to be fiber. In turn, for fiber to be able to serve this need, the fiber domain needs to be aware of what happens in the wireless domain.
So here you're talking about multiple base stations or multiple antennas that are serving a single user, and the base stations are interacting in some intelligent way? So
your question is actually very much to the point. It can be a single base station with multiple antennas, so it can be several different base stations that are coordinating their transmissions. There is a slight difference between these two. But the important point is that in both cases, if we want to gain high efficiency, and we can, certainly that is well recognized now in the wireless community, what you have to have is a much more powerful backbone behind the wireless network. And that backbone will be clearly optical. So that is just one example of how these two domains can help to each other. Okay. So other forms of collaboration may be when you would redirect traffic from one heavily loaded cell to an adjacent cell that is less heavily loaded. It's another example of collaboration.
Okay, and that intelligence would need to reside in
where, right?
Yeah, exactly.
So that is one of the many open questions where that would be, right? So in some, that is one important research area. It might be distributed, or there might be a centralized sort of command and control center, kind of a supercell that would coordinate these transmissions. That is one of the many open questions. Also, it's a question of how much you would communicate between these points. It can be shown quite easily that the most powerful form of collaboration is achieved if somewhere, let's say at the central command point, you would have knowledge of complex amplitude, in other words, both amplitude and phase, of all transmissions of all coordinating access points. Now that is an enormous amount of data. And the only medium that can transport this data efficiently would be, obviously, fiber networks.
I suppose that depending on the size of the cell, you might be talking about a large number of users at one time.
Right.
Right?
Right. It might not be necessary to transmit information about all users. For example, if you have a user that is very close to a single access point or to a single antenna of an access point, there isn't much to be gained probably from collaborating with more remote antennas. But if you have a sizable number of users that sits somewhere in the gray area and has, let's say, roughly the same distance from 3 or 4 antennas, then that number of users can gain significantly if it can utilize all the antennas it has access to.
Okay.
So it's kind of common sense, right?
Right.
Intuitively it's felt.
Right. So is this, does this become just a mathematical problem of understanding what's happening at each base station and coordinating all the different users to all the capacity that's needed, or are there problems in physics to overcome that?
So there is a huge number of problems here. That entire area is still pretty young. But let's begin with the whole process. Let's just look at the various steps involved in all this happening, right? So let's say, just for simplicity, that you have 3 antennas, and let's think for a second that you have just one user in the middle, and we want to ensure collaboration between these 3 antennas, so that their signals talking to the same user would reach that single user in phase, because if not, they would cancel each other, right? What needs to happen here? Well, for one thing, these antennas would need to find out how far that user is, what is the phase, not just the amplitude, but the phase of the electromagnetic wave reaching both antennas and the user. They would need to transmit that information to the command, to the coordinating point, and they would need to decide between them what is the optimum way to proceed. And that needs to happen for all users for whom you want to provide this capability. So the amount of information that you need to exchange is humongous here. So if you look further beyond the scientific principle, right? So in addition to deriving algorithms for all this happening, right, you must start thinking about the network architecture and the computing architecture and the protocols needed, to make it all happen.
Right.
And we are very early in this game. So
Right.
it's,
Of course, the service providers are racing forward at this very moment to build out their networks as quickly as they can and find the best places for putting the base station. How should they be thinking about this if the network architecture is evolving?
Yeah, that's a tough question indeed. It's a moving target, you're absolutely right. I think in actual reality, of the denser is the network. In other words, the more antennas they can place, the higher the bandwidth they will be able to provide. It's a very simple mechanics. Smaller cell sizes will lead to better coverage and to higher bit rates ultimately. So that's pretty much independent of the technology. So even with assuming a current level of development of technology, however good you are, you will be still much better off if you have a larger number of antennas per square mile. Now, in many cases, we might be progressing toward the situation where every single geographical unit, and that may be as small as this room, would be a single cell, maybe even with multiple antennas. So for example, if in this room we could place 4 antennas in each corner of this room, right? That would be terrific, not only in terms of bandwidth, but also in terms of energy efficiency, which is the second topic we wanted to discuss.
And would these base stations, being so many of them out there, would they need to be intelligent in some way? Do they need to have the processing capabilities with them, or is that all brought back in a centralized point of the network?
So that's another issue that is very much under intensive investigation. Both options are feasible, right? You can have a centralized control, and you can have distributed control, and there are people who are arguing both cases, of course. My own gut feeling is that we will end up with a hybrid architecture where some independence will be preserved to individual base stations, and some degree of control is sitting at the central side. From this point of view, I frequently see some similarities between network architectures and political world, right? If you look at the United States, you have federal government that has a certain authority. You have state governments that have less authority, but still a sizable amount of authority, right? And so on, right? And you have local governments and so forth. So something very similar, I think, will take place here as well.
So there's, of course, a lot of work underway in software-defined networking, where the whole network could be reconfigured on demand. Do you see that playing a role in this hybrid architecture?
Well, absolutely, absolutely. It's clear that software, which is already playing an important role, will play even more important role in the future. And that's on all levels of technology, beginning from very low level signal processing, sitting close to the physical layer, and up to and including network management. That is pretty clear. You know, one of the things I learned when establishing a company more than 10 years ago was that in many cases, probably in most cases, I would guess, when you have a networking company that actually makes networking equipment, you're going to have more software people than hardware people. It's a complete reversal from what it used to be, let's say, several decades ago. So it clearly teaches us something about where the center of gravity is in this field.
Right. While we're talking about network architecture, there's also a lot of work underway to improve the efficiency of networks, the energy efficiency of networks. Where do you see the big opportunities in that area, the opportunities to improve the power efficiency?
Right. So one area that attracts a lot of attention is data centers, obviously, because each one of them consumes an enormous amount of power. There is a generic term to describe it, big data, which is associated with big power needs, right? So, and everybody knows these famous examples when big corporations are placing their data centers further to the north to ensure cooler temperatures around itself. So that is kind of an obvious example, and a lot of important and useful work is being done and will be done there. What is perhaps less broadly realized is that actually more energy is spent on the other side of this pipe. Because you must remember that this data that is accumulated in the data centers comes from somewhere. So where does it come from, right? It comes from office buildings such as this one. It comes from our individual homes. It comes from a largely distributed rest of the society. So the reason people are not thinking about it too much because it is distributed. But it it's quite easy to evaluate the relative amounts of energy. And actually, is more energy spent outside of the data centers than within them. So it will be equally important, or perhaps more important, to reduce that amount outside of the data centers. And that's, by necessity, a more difficult problem. And I'm saying it is more difficult because it is a much larger, both geographically, politically, distance-wise, in terms of degree of control and so forth, field than the data centers themselves. Okay. It's much easier to design, in a sense, a new data center than to change the structure of the society so that the other side of the equation would be also reducing its power needs while simultaneously increasing bandwidth, because the hunger for bandwidth is not going to diminish. It's going to become even stronger, perhaps. So we are faced with an interesting goal where we need to continue to push for higher bandwidths, but simultaneously we need to reduce the needs to energy, at least on a per bit basis, and preferably even in the aggregate sense.
Okay. Are there any interesting research projects in this area that you might like to highlight?
Yeah, there are quite a few. Obviously, I'm best aware of the ones I'm running in my own group. So we have a number of these projects. One we are running with Alcatel, and that one is aimed at reducing the energy needs of individual homes. And by energy needs, I mean in the IT domain, not in the area of heating or ventilation. And we have a companion project we're running with Corning that aims to reduce energy needs of office buildings. And again, by energy means, we mean energy needs of IT within these buildings. That is actually very interesting because the architecture of office buildings in terms of IT is actually quite complex. Not a lot of people realize it, but it's a very powerful network that moves around a lot of data. And the number of office buildings, both in the country and around the world, is huge. It's much larger than the number of these big data centers. So it's a very important problem to understand and to solve correctly. So that is the second one. The third example I can bring, again from our own research program, is a joint project that we are running with NSF sponsorship jointly between my group, MIT, and UTD. That one is called Ultraflow. And that one has a slightly different goal, but it is not orthogonal. It's essentially a tightly related goal. We're looking into the opportunity or into the possibility of changing the entire architecture of data transfers in such a way that one wouldn't need to go through that many routers, so that you would be able to, let's say, download the movie from one computer, let's say from a server, into your own computer, while bypassing the many routers along the way. So that is a very ambitious goal, and not everybody agrees that it is doable, which I think is a good sign that it's a good research project. And all these things are interrelated, but simultaneously other things must be addressed. People are working concurrently on reducing energy consumption of ICs. That is typically achieved by reducing the size of each individual component, reducing pushing further and further toward smaller and smaller line definition on a wafer. There is a nice push toward more energy efficient software. You certainly can improve your protocols to reduce energy consumption. And a good example would be sleep mode. Various parts of your circuitry or of your network or of your node, if they are not used at the moment, they can be put asleep. One challenge with all of them is that yes, you can certainly do that, and it's not even that difficult. The fundamental problem is that you don't want to lose performance, because if it is asleep, you must be able to wake it up quickly enough so that the fact that it is asleep wouldn't impair your network performance.
Right.
So that is a very difficult trade-off. We have had a nice research project going in that field, so we gained a lot of appreciation of just how powerful this technique can be, but also just how difficult it is to design a viable solution.
Right, right. So the networking field remains a very fertile one.
That's exactly right, yes. There is a lot of work to be done here. Also important to stress that there are many players in all that. We are talking so far about network, but network, we must remember, is only part of the total equation. So the data that you are transmitting from this network comes from somewhere, and it is being delivered to somewhere. So for example, if you're downloading a movie from a server, then one part of the equation is the server itself. So if you're just optimizing the network, but you are allowing the server to consume a lot of energy, then once you download it, you view it on a power-hungry TV set, then there isn't much you can do. So we must do our job within the networking domain. Other people will do their own in the area of displays, TV sets, servers. So all these goals will need to be addressed.
Excellent. Well, thank you very much for joining me today.
Thank you.
I appreciate it.